this intro paragraph or few paragraphs is just in general, we always need a balanced equation. So that's why we've already gone through balancing equations, because that balanced equation allows us to convert between substances. So what we'll actually do is we can actually flip to the back of the first page. All right, and the back of the first page says simple mole ratios, and we have some of this information at the top. Now, units 5 and unit 6, we've already gone through. Unit 5 was mole conversions. How did we convert between grams and moles and particles? If you don't have this written down somewhere, and maybe you want to write it at the top, right? Maybe you want to write it up here in the corner of your discussion. If you don't have this written down, make sure you have that, right? You write that down. This is how we went from one unit to another in Unit 5. Right? In Unit 5, we converted between grams and moles, between moles and particles, and even from grams all the way to particles, right? Or vice versa. And I use different colors here just to be able to distinguish between the different conversions that we can do. Remember, moles always was that middle unit that we had to go to. So when you wanted to go from grams to moles, we had to use the molar mass. You're still going to need your green periodic table because we're going to be using molar masses as we convert. So your green periodic table is going to be useful. And then to go from moles to particles or the other way, we use Avogadro's number. When we say particle, that could be atom, molecule, formula unit, any small particle. And we use Avogadro's number. Remember, Avogadro's number is up on that box on top of the bookshelf. You always have Avogadro's number. But that allows you to convert between moles and particles. We could never go directly from grams to particles. We always had to go to moles in between. We're going to follow that same idea as we go through stoichiometry, as we look at converting from a reactant to another reactant or a reactant to a product. And then we also looked at predicting products, writing formulas, balancing equations. We're going to take all of this information that we did in the last 2 units and apply it to stoichiometry. All right, everything continues to build. And so balancing equations is important because the coefficients give us the number of moles of everything. Those coefficients are basically kind of the recipe for that chemical reaction. So we're going to be using the skills that we used in Unit 5 and Unit 6 and kind of combine them all as we look at stoichiometry. So stoichiometry is just determining how much product is made, how much reactant is needed during a chemical reaction. And there are the same 4 steps that we follow for every problem. It's these 4 steps, and you have these 4 steps typed right at the, top to middle of your page. So we're going to follow these 4 steps every single time, and we're going to use these 4 steps as we go through examples. So you always need to make sure, first and foremost, you have a balanced equation. You need to make sure you have a balanced chemical equation for the reaction in the problem. If it's not balanced, you need to make sure to balance it. Now, if you notice that you have a reaction that already has coefficients, I'm not tricking you. Okay? If there's coefficients, it's going to be balanced. If there's not coefficients, or if in parentheses it says balance the equation, make sure you balance it. Once you have your your balanced equation, then whatever given information you have, just like we had to do up here, make sure your given information is in moles. If it's not in moles, convert to moles. Then we use the mole ratio to go between substances. So that's why that balanced equation is important. We use the mole ratio to go between substances. So what we did before is we just went between grams, moles, and particles of the same substance. Now we're looking at how could we go between substances. So if I ask you, if you burn 12 grams of methane in the lab, how much carbon dioxide are you producing? That's a stoichiometry problem. You're going from one substance to another. And then lastly, if the problem wants something other than moles, you have to convert back out to moles. So these are the 4 steps we're going to use every single time. As we go through these examples, I'm going to come back to these 4 steps every time. So if we take a look at the example, so example 1 is at the bottom. We're going to go through example 1 together. I'll have you try example 2 with a small group, and then we'll kind of go back and forth like that. You will want a calculator, so if at any point you need to get up and grab one of my calculators, you can. You will need a calculator for the rest of this week. So make sure if you have a calculator, maybe you just didn't bring it today, bring your calculator. And so as we go through these examples, I'm going to kind of follow this format just to help us be able to identify information. Always underline your given information, so your number and your unit that you're given, and circle what you're trying to find. Then we'll go through and we'll solve. So let's look at example 1. Now this is just moles to moles. So we're going to kind of start with the most basic example, and then we're going to work out to a little bit more difficult ones. So this is hydrogen sulfide gas, which smells like rotten eggs, burns in air to produce sulfur dioxide and water. Notice we have an equation down here already. How many moles of oxygen gas? So I'm going to go ahead and circle moles of oxygen gas. That's what the question's asking for. My answer should be moles of oxygen. Would be needed to completely burn 8.65 moles of hydrogen sulfide. So notice that I'm not only underlining the number and the unit, but I'm also underlining the substance. This is the best way as you start getting into these stoichiometry problems to kind of organize your information. I like doing this as well. So 8.65 moles of hydrogen sulfide. Well, if you look at this balanced equation, the only one that has hydrogen and sulfur is H2S. So underneath H2S, I'm just going to put 8.65 moles. That's what the problem tells me. We're burning 8.65 moles of hydrogen sulfide. And it wants to know how many moles of oxygen gas would we need. So I'm going to put a question mark with moles, because the unit that it wants is moles. It doesn't say anything about SO2 and H2O, so that's not my focus for this problem. Now, as we go through the stoichiometry steps, step 1 was to make sure you have a balanced equation. All right, here it is. Here's our balanced equation. Step 2 is to take your given information. So my given information is 8.65 moles of H2S, hydrogen sulfide. Is my given information already in moles? Yeah. Your given information is already in moles, so you don't have to worry about converting. So step 2 is done. Now step 3, this is the new part for us. We need to go from H2S to oxygen gas, O2. To go between substances. So I left this little gift tag up here on the board. Remember, whatever you're going from is on the bottom, whatever you're going to is on the top. Make sure that our units cancel. When you want to convert between substances, it has to be in moles. So I want to cancel out moles of H2S. I want to go from moles of H2S, and the substance I'm trying to get to is oxygen, O2, which means I'm going to go to moles of O2. This is the mole ratio. The only way to convert between two substances is through the mole ratio. The numbers that you get for the mole ratio come from the balanced equation. That's why you need to make sure your equation is balanced. So for every 2 moles of H2S that react, we require 3 moles of 3 moles of O2. So for every 2 moles of H2S that react, we require 3 moles of O2. Now look at our units here. Moles of H2S was on the top here. Moles of H2S was on the bottom here. Now the unit that I'm left with is moles of O2. This is why writing this underneath helps. The question wants to know how many moles of O2. I'm at the unit that they want. So now I can go ahead and just solve. So to solve, remember your given information is not over anything. If you want to put it over something, it's just the number 1. No unit here, nothing else, just the number 1. But this is a numerator. So you do 8.65 times 3 and then divide by 2. So 8.65 times 3 and then divide by 2. If you keep it to, I guess, 3 significant figures, you'll round it. So not rounded, you get 12.975 moles of O2. Be specific with your units. It's not just moles, we want to be specific. It's moles of oxygen gas. It's O2 because oxygen is diatomic. If you want to round, let's say I want to round to 3 significant figures, 1, 2, 3, I would round here. But that 9 doesn't stay in 9 because of the 7, it moves up. So this would actually be 13.0 moles of O2. I'm not going to be super picky on significant figures. If you keep it as 12.975, that's okay. What I am going to be picky about, though, is making sure that you have those units. Notice how I had units throughout this entire thing. Show how it cancels. When you want to go from one substance to another, it has to be in moles. So if we look at number 2, we'll just kind of circle, underline, label, and then I'm going to have you set up number 2 with a partner. So propane burns in air. So you have a propane, like a blowtorch, that's propane. When it burns, it forms carbon dioxide and water. If 12.5 moles of carbon dioxide, there's given information, a number, a unit, and a substance. 12.5 moles of carbon dioxide are formed. How many moles of oxygen were used? So again, I like setting up my information like this underneath the balanced equation, just so that everything's there. So 12.5 moles of carbon dioxide was produced. How many moles of oxygen was used? So now this says nothing about propane, nothing about water. Our focuses here are carbon dioxide and oxygen. So see if you can use example 1 kind of as a guide and work with a partner. See if you can set this up and solve. All right, talk to each other as you're setting it up. See if you're getting the same thing. But use example 1 here as a guide. It's going to be a very similar example. If you go through those 4 steps, you'll find that some of them is already done for you. So you're starting with your given information. A couple of those steps in the 4 steps that we always do. You already have a balanced equation here. Step 2, if you write down your given information, your given is already in moles. You don't have to worry about converting. Then to go from one substance to another, it has to be in moles. The reason it has to be in moles is because that is what each of these coefficients tell us. The ratio of moles of substances. So based on this, we had moles of CO2. That goes on the bottom so that it cancels. Moles of oxygen goes on the top. The way that I can read this is that for every 3 moles of CO2 that is produced, we require 5 moles of oxygen to react. So the mole ratio is 5 moles of O2 to 3 moles of CO2. Now moles of CO2 cancels, we're at moles of O2. That's what this wanted. It wanted moles. So we're done with conversions, and then we just multiply and divide. So 12.5 times 5, and then divide by 3. You could do, if you wanted to go out, again, I'm not going to be picky with significant figures. You get 20.83. If you wanted to just round to 20.8, that's okay. This is not your answer. If you just wrote this down, you wouldn't get full points. You have to make sure you include the unit, so moles, and the substance. So it's 20.83 moles of O2. So these are questions where you don't have to actually do as many extra conversions. Right? We're not using these conversions that we learned before because our given information is already in moles. Our answer should be in moles. Questions on either one of these examples with just moles to moles. So let's look at what happens if our given information isn't in moles or the unit that they want isn't in moles. So if we look at example 3, so if you read through example 3, this is on the back of the first page. There we go. All right, so example 3 up here at the top. You eat 90 grams of glucose. That's 45 M&Ms. So you're hungry, you want a snack. You eat 45 M&Ms. That's 90 grams of glucose. Now, I tell you here glucose is C6H12O6. Right? You wouldn't have to know some of those like glucose, things like that. I would give that to you. But if glucose reacts with oxygen gas to produce carbon dioxide and water, how many moles of oxygen will you have to breathe in to burn the glucose? So I know that I'm solving for moles of oxygen, so I'm going to put a question mark with moles underneath O2. That's what I'm trying to find. My given information up here is 90 grams of glucose. All right, so 90 grams. Now let's go through those 4 steps. Do we already have a balanced equation? Yeah, right here's the balanced equation. You have some coefficients. It's balanced. Write down your given information. So 90 grams of C6H12O6. Please put the unit and the substance. That will help you. Is this unit that I wrote down moles? No. So now we're looking at what happens if our given information isn't in moles. So you have a balanced equation. Make sure your given information is in moles. So now what we're going to do is we're going to go back and use what we learned before to go between different units. So I don't want grams, right? I want grams to cancel. I need to go from grams to moles of C6H12O6. I need to go between grams and moles. Well, if we look up here at how we can convert between the units, remember to go between grams and moles, we need the molar mass. So what I'm going to plug in here is the molar mass. And remember that the molar mass comes from the periodic table. The molar mass is a certain number of grams for every 1 mole. Now, just a review of calculating molar mass, I'm going to do it up here so it's kind of out of the way. To calculate the molar mass of glucose, which is C6H12O6, to find the mass of 1 mole, you add up all the masses from the periodic table. There are 6 carbons. So 6 times 12.01 plus there are 12 hydrogens. So 12 times 1.01. And there are 6 oxygens. 6 times 16. So in my calculator, I put them all in parentheses. So I did parentheses 6 times 12.01. I closed the parenthesis plus 12 times 1.01, close the parenthesis, plus 6 times 16. And when I did that, I got 180.18 grams per mole. That is the molar mass of glucose. Again, molar mass is grams per mole. So that means there are 180.18 0.18 grams in 1 mole. Now here, the grams cancel. Now I'm at moles of glucose. So now I've converted my given to moles. Again, the importance of converting your given to moles is that now you can convert between substances. So I need to go from moles of glucose to moles of whatever the other substance is. This has to be in moles. So again, this is the mole ratio. The reason it has to be in moles is because if we use our balanced equation, that gives us the ratio of moles. Now my goal is to get to oxygen, so I'm going to go moles of O2. The numbers from the mole ratio come from your balanced equation. So for every 1 mole of glucose that we burn, we need 6 moles of O2. Now moles of glucose have canceled. One's on the top, one's on the bottom. You're at moles of O2, that's what we want. So now you multiply across the top. 90 times 6, I'm ignoring the 1 because it's a 1. So 90 times 6, divide that by 180.18. And when I do that, I get 3 moles of O2. And if you want to make sure that that's going in your calculator correctly, right, 90 times 6, hit enter, just hit divided by 180.18. Just be careful with rounding. So this one, our given was not in moles. We had to convert. In order to go between substances, you always have to go to moles in between. Let's take a look at it, just example 4, and then we'll continue looking at these tomorrow. So example 4 says, how many grams of oxygen gas? So I'm going to circle that. Grams of oxygen gas are needed to react with 0.521 moles of iron. So I'm circling what I'm trying to find. I'm underlining what I'm given. I'm going to do the same thing. I'm going to label underneath the balanced equation. So 0.521 moles of iron. And my goal is to get to grams of oxygen gas. It's O2 because oxygen is diatomic. That's why it's O2 there. Now again, let's go through the 4 steps. Always work through those 4 steps. Do we have a balanced equation? Yes. Okay, write down your given information. 0.521 moles of Fe. Is this in moles? Yes, I wrote down moles of iron. So it's already in moles. So step 2 is done. Step 3, convert between substances. The reason it's important to have your given information in moles is so that you can go from your given to something else. When you go between substances, this has got to be moles and moles. We cannot use any other units in this mole ratio. It's called a mole ratio. Right? Not a gram ratio or a molecule ratio, but a mole ratio. Because that's where these coefficients come in. So it's moles of iron on the bottom so that it cancels. For every 4 moles of iron, how many moles of oxygen are required?
3.
3. Right? Comes from the coefficients. So now, moles of iron have canceled. We're at moles of oxygen. What I wrote underneath here, do I want moles as my final answer? No. Right, my final answer, we want grams of oxygen. So now we have to actually do that 4th step, which is taking moles of your new substance and going back out to a different unit. So right now I'm at moles of O2. Right? Moles of iron have canceled. I'm at moles of oxygen. I don't want moles of oxygen. I want grams. So that means that moles of O2 is going to go down here on the bottom, again, so that it cancels. I want grams of O2. Here is why writing the substances are also useful, because now I can see exactly what I'm working with. Remember, to go between grams and moles, this is the molar mass. I have this written up here. The molar mass is a certain number of grams for every 1 mole. The 1 always goes in front of mole with molar mass and with Avogadro's number. So for 1 mole of oxygen gas, there's a certain number of grams. Now notice how this is O2. Oxygen gas is O2, not just O, which means it's 2 times the mass of 1 oxygen from the periodic table. Right? 2 times 16 is 32 grams per mole. Because we're dealing with O2, it's 32 grams. So now moles cancel. Now I'm left with grams of oxygen. That's what this problem wanted, and now we can solve. So now we multiply across the top. So now we're actually doing 0.521 times 3 times 32, divide by what's on the bottom. Again, this is a 1. We can ignore it. So really just divide it by 4. All right, and when you divide it by 4, you get 12.504. And again, make sure you have unit and substance. Whatever we didn't cross out, there's our unit. Grams of O2. So for example 5, as we go through these examples, remember we have 4 steps that we go through every time. And so the 4 steps that we go through are on like the back of the first page of the discussion. We talked about this yesterday. 4 steps is to make sure we have a balanced equation, make sure our given information is in moles, convert using the mole ratio, right? Can't be grams, has to be moles, and then we go back out to whatever unit it's asking for. So if we look at example 5, this says how many grams of ammonia? So I'm going to always circle what I'm trying to find so that it's easy for me to find when I reread the question. Can be made when 5 moles of hydrogen react with sufficient nitrogen gas. So I have a balanced equation here. Underneath the balanced equation, I'm just going to put what I know and what I'm trying to find just to help me as well. So how many grams of ammonia? Ammonia is NH3. So I'm going to put a question mark with G for grams. Can be made when 5 moles of hydrogen. So this is 5 moles. Notice it's H2 and N2 because they're diatomic, so when they're by themselves, they get that 2. It doesn't say anything about nitrogen, so that's not our focus. Our focus in this problem is H2 and NH3. So step 1, we have a balanced equation. Step 2, let's write our given information down. So 5.00 moles of H2. You want your number, your unit, and your substance. So 5 moles of H2. Step 2 is to make sure that our given information is in moles. This is already in moles. All right, so we're good. Then, to go between substances, it has to be the mole ratio. So I want to go from hydrogen to ammonia. To go from one substance to another, it has to be moles because these coefficients from the balanced equation tell us the number of moles that are needed to react. So this tells us for every 3 moles of hydrogen that react, for every 3 moles of H2 that react, 2 moles of NH3 are produced. This is the mole ratio. Lets us go between substances. That's the only way we can convert between substances. So notice how moles of H2 cancels because it's on the top and then the bottom. Now we're at moles of NH3. This is why I like putting directly underneath what we're trying to find. So step 4 in a stoichiometry problem is to convert to whatever unit the question is asking for. Once we use the mole ratio to find the new substance, then we might need a different unit. This question doesn't want us to solve for moles, it wants us to solve for grams. So right now I'm at moles of NH3. I don't want moles of NH3, I want grams of NH3, so we have to keep going. Now moles of NH3 is on the top. That's not the unit that I want, so it's going to go on the bottom. If we think back to our mole conversions that we did before, grams to moles to particles, we have a way to go between all of those units. I don't want moles, I want grams. We have a way to go between the two. To go between grams and moles, we have to use the molar mass. So I do have a way to go between moles of NH3 and grams of NH3. I need to use the molar mass to convert between those two units. Between grams and moles is always the molar mass. And if you notice what we wrote down, there's a certain number of grams for every 1 mole. That certain number of grams comes from your periodic table. So this is NH3. You have to use your periodic table and figure out what's the mass of NH3. So for NH3, there's 1 nitrogen, which is 14.01. And there are 3 hydrogens, which is 1.01. So 14.01 plus 3 times 1.01 is 17.04. The molar mass is just adding up from the periodic table. Molar mass is always 1 mole, just like Avogadro's number is always 1 mole. So notice how units, again, cancel. When one is on the top and one is on the bottom, they cancel. That's the whole point of doing dimensional analysis. So our given was in moles. We canceled it out, went to a new substance, canceled it out, went to grams. Now we multiply across the top. Divide by what's on the bottom. All right, so you multiply across the top. 5 times 2 times 17.04. Divide by 3. We get 56.8. Look at what unit we didn't cross out. That's the unit of our answer. Grams of NH3. So all we were focused on in this problem, all we were focused on was hydrogen and ammonia. We didn't care about nitrogen in this. It didn't give us information. We don't care about it. With stoichiometry, you're always looking at 2 substances. You're given and then what you're trying to find. Now let's look at example 6. This is going to help us for the lab. Because in the lab, we're going to be doing a gram to gram calculation. So for example 6, again, I'm going to go through the exact same way I did. How many grams of water, okay, so grams of water, water's H2O. So I'm going to put a question mark with grams underneath H2O. Just a way to organize my information. How many grams of water can be made from burning 32 grams of methane gas? Methane is CH4. So I'm going to put 32 grams underneath CH4. This said nothing about oxygen, nothing about CO2. Like, I really don't care about these 2 substances for this stoichiometry problem. Our focus here is going between methane and water. So let's say that you were to open the gas jets and you lit a match and you burned 32 grams of methane gas. We can figure out how many grams of water we made. That's what this problem is asking. So let's start by writing down our given information. 32 grams of CH4. Having the substance helps because then, 1, it helps you for molar masses if you need it, and 2, it helps you when you're looking at your balanced equation. So here's my given information. Is this in moles? No. So we have a balanced equation, right? Step 1, check. Step 2, write your given, make sure it's in moles. It's not in moles. So that's what we need to do first. Put your given information in moles. And if you say, what's the use of putting it in moles if we're going from grams to grams? Whenever you use the balanced equation, that is moles. That is not grams. So we need to start by converting grams to moles. We look at our mole conversions that we've been doing. We can go directly from grams to moles. I'm going to put grams of methane on the bottom, moles of methane on the top. So again, if we think about that gift tag, the unit you're going to is on the top, the unit you're going from is on the bottom. We're going from methane, grams of methane, to moles of methane. When you want to go between grams and moles, that's molar mass. Molar mass is always a certain number of grams for 1 mole. A certain number of grams for 1 mole. That certain number of grams, this comes from the periodic table. So if I look at CH4 from the periodic table, carbon is 12.01 plus 4 times 1.01. Is that 4.04, 16.05? Molar mass of methane is 16.05 grams. Again, if you said, how did you do that? I looked it up on the periodic table over here. Right here's the molar mass. And if you remember the units, it's grams per mole, which means it's 16.05 grams for every 1 mole. That's why we can use that as a conversion factor. So now, my given information is in moles. Grams has canceled, now I'm at moles. Now we can go from one substance to another once we're at moles. You have to use the mole ratio. Right, now I'm at moles of CH4. That's going to go on the bottom. That's what we want to cancel. I want to go to water. So the 2 substances we're focusing on is methane and water. For every 1 mole of methane that we burn, because if there's nothing there, it's assumed to be a 1, we produce 2 moles of water. For every 1 mole of methane that we burn in the lab, we produce 2 moles of water. So now moles of CH4 have canceled. Again, this is the mole ratio. This allows us to convert between 2 different substances. Moles of one substance to moles of another. So now if you look at how our units are canceling, we're at moles of water. We don't want moles of water though, we want grams of water. So now we have to actually go back out to a different unit. You always go to moles in between, so you can use the mole ratio and then go back out to a different unit. So moles of water is going to go on the bottom. Again, top and bottom will cancel. We can go directly to grams from moles. That's molar mass, just like we did here. So now this is the molar mass of water. It's not going to look the exact same though. Remember, molar mass is grams per mole. It is always grams per 1 mole. Notice how here the 1 went in front of mole, down here the 1 goes in front of mole. Because the unit of molar mass is grams per mole. So if we look at water now, 2 times 1.01 plus 16. So the molar mass of water is 18.02 grams per mole. That means for every 1 mole of water, it has a mass of 18.02 grams. Now again, notice how this cancels. Moles of water is on the top, moles of water is on the bottom. The unit that we are left with that we have not canceled is grams of water, which is exactly what the question asked us for. Example 6 would be one of the more difficult questions going grams to grams, because you have to go through all of the steps. You convert your given, you use the mole ratio, and then you have to convert back out. So if we put this into our calculator, 32 times 2 times 18.02. I'm ignoring the ones because anything multiplied by 1 is that same number. Divided by 16.05. I got, maybe if I can do this, 71.9. Again, look at what units I was left with. It's the same thing as what unit it asked us for. How many grams of water? So 71.9 grams of H2O. So again, example 6 is probably one of the more difficult types of questions, but it's one that requires us to use conversions to go between everything. Questions on this before I scroll up to example 7? So the last example is example 7. If you read example 7, if 12.6 grams of sodium is added to water, how many molecules of hydrogen gas will be created? So if we read through this again, we're going to do the same thing that we've done before. Circle what you're given, underline what you're given, circle what you're trying to find. And if you have a different way, if you like highlighting or using different colors, whatever works for you. I just try to give you some strategies to make it a little bit easier to follow some of the, some of these problems. So let's go through this one. 12.6 grams of sodium. That's given information. It's a number, a unit, and a substance. So 12.6 grams of sodium is added to water. How many molecules of hydrogen gas will be created? So now I'm going to go to H2. Remember to distinguish between moles and molecules. I'm going to use MOLEC for molecules. Some people will use MC. Whatever unit works for you, as long as you can distinguish between your moles and your molecules. So it says nothing about water, nothing about NaOH. My focus in this problem is going between sodium and hydrogen. It's H2 because hydrogen is diatomic. So let's go through the 4 steps. Step 1, do I have a balanced equation? Yeah, it's given to me right here. Step 2, write down your given information. 12.6 grams of Na. Is this in moles? No. First thing you need to do is convert your given to moles. Some of my classes start to say, like, when in doubt, go to moles. Like, if you're not sure, convert it to moles. To go between the two, I don't want grams of Na. I want to get to moles of Na. I want to take my given information and I want to convert it to moles. For every 1 mole of sodium, there's a certain number of grams. To go between grams and moles, you use the molar mass. Look at your green periodic table. Molar mass of Na is 22.99. This comes directly off the periodic table. This is just a single element, so you can look right at the periodic table. So grams of Na cancels. Now, my given information is in moles. Once your given information is in moles, the reason that you want it in moles is so that you can convert between substances. I want to go from Na to H2. I want to go from one substance to a completely different substance. To do that, you have to use moles. Because the coefficients in front of each substance in the balanced equation tells you how many moles are required. So what this balanced equation tells us is that for every 2 moles of sodium that react, 1 mole of hydrogen gas is produced. 1 mole of H2 is produced. So now moles of Na cancel, and I'm at moles of H2. This question, though, doesn't want moles. This is why it's important to distinguish. If you look at my answer keys, you're going to see MOL for moles and MOLEC for molecules. We don't want moles. We want hydrogen, but we don't want moles of hydrogen. We want molecules. So I want to go from moles of H2 to molecules of H2. And if you look at our mole conversions that we did before, I can go directly from moles to molecules. A particle is an atom or a molecule or a formula unit. But to go between a mole and a particle, you always have the box up on the bookshelf. You use Avogadro's number. 1 mole of a substance is Avogadro's number of molecules, 6.022 times 10 to the 23rd. All right, so I'm going to put Avo's number. Now, moles of H2 cancel. Notice what I'm left with. I'm left with molecules. That's what I want. To plug this in your calculator, you have to use that exponent button. If you have a calculator, looks like mine, or even a graphing calculator, you'll do 6.022 second EE, 23. So in your calculator, it would look like this, 12.6 times, I ignore the ones. If you like putting the ones in, put the ones in. It's going to look like this, 6.022 E23. You don't do the times 10. That E takes place of times 10 to the. So 6.022 E23. And then if you want to do this all at once, you need to make sure to put what's on the bottom in parentheses. So 22.99 times 2. So 12.6 times 6.022 E23 divided by the quantity 22.99 times 2. Make sure you look off to the side when you get your answer. On one of the smaller calculators, you'll notice this times 10 over to the side and then the exponent. If you have a graphing calculator, you'll just see that E. That E means times 10. You get 1.65 times 10 to the 23rd. And then your answer with units is molecules of H2. So examples 6 and 7, these are the two that are, I would say, the most difficult because you have to take your given information, convert it to moles, and then you also, once you use the mole ratio, have to convert back out to a different unit. So tomorrow we'll be doing more practice with this. Probably tomorrow and Friday we'll be going through more practice with this so you can really make sure that you've got it. And then next week we're going to spend a lot of time doing lab where you can actually do the stoichiometry, right? Do the math and then compare it to lab.